Hello everyone, my name is Hassan, and welcome back to another Data in the Wild episode hosted by Data Meaning. Before we begin, don't forget to subscribe to the channel below and click the bell to turn on notifications to be the first to know every time we upload a new video. Today we're going to talk about logistic regression. Logistic regression is a statistical method for classification, and it's an extension of linear regression where we use the same equation used in the linear regression and plug it into a transformation function that maps our continuous value, into a discrete one, kind of discrete one between 0 and 1, which is a probabilistic evaluation or estimation of classes of prediction we might have. And this transformation function have this form of a sigmoid function that can take those values and map it into a value between 0 or 1. So we might have 0 0.2, 0 0.4, 0 0.6, like a probability estimation of things. And in this equation over here, we're replacing x with the equation of linear regression with the weights that needs to be updated. And in order to update those weights, we need to have or to define a cost function which we can accordingly set the right value of those weights. And the cost function consists of two main equations. One, in case of if we are predicting of y equal to 1, or 1 can be a certain different class, but we're just doing this numerical representation. So in case we're predicting 1, we need to compare to something like the graph showing in blue. So if the estimated value is 1, which is over here, the cost function, which is represented by the y-axis, would be minimal. And if the prediction was 0 and it should be 1, so the cost would be at its maximum value over here. And the same is true in case we're predicting for y equal to 0. And this function is capsulated into one equation in this form. So if we're having y equal to 1, we're working on y equal to 1, we need to keep only this minus log h theta of x. So if we replace y by 1 over here, we're gonna be multiplying this by 0, and it's like omitting this observation. And the same thing is true in case we're working with y equal to 0, so we'll be omitting this part of the equation, the first term, which is related to y equal to 1. And now let's jump into the technical implementation of this logistic regression algorithm, and we'll be working on the social network ads CSV file that we have checked before. So if you check it over here, we're having the age and the estimated salary and whether a customer have done a purchase or not. It's a binary classification by a 0 or 1 for the purchase column. So first we're gonna import the libraries. We always need to load them, the NumPy, Matplotlib, and Pandas, and we're gonna load it into a dataset variable through Pandas library. And we're gonna use we're gonna set x or the independent variables to be only the age and the estimated salary, and y is the last column in the dataset which is purchased, and extract the values from it. So if we run this one over here, and then we're gonna do the model train test split, where we split it between training and testing partitions using a test size of 75% for training and 25% for testing. So we're gonna end up having this is for x train, y train, and y test. This is clearly for the y for the dependent variable, because we're only seeing values of zeros or 1. And because we're using those two different scale independent variables, the age and the estimated salary, we're gonna do feature scaling for both training and testing. So we apply it using a sklearn standard scaler by transforming fit transform. So fit transform actually applies the transformation and fitting to get the right transformation equation for the values on the same so it returns back the same input we're using. And then we're gonna fit the logistic regression imported from the sklearn linear model. We're gonna fit the X train, Y train, and predict new results. Let me just run it over here. So we check it for the testing data set, and over here we're gonna use the confusion matrix to assess our accuracy, which is 89% or 0.89. And here's the visualization for the training part. So you can see this separator between the ones and the zeros, and you can still notice those error over here for values that were misclassified. So you can see the green ones in the red area and the opposite also. And this is for the testing data set. Of course, we're having fewer observations compared to the training one, but still an accepted value of error we can observe. Thank you for watching, and stay tuned for another video on machine learning algorithms.
If you have any questions or suggestions for future videos, please comment below. Don't forget to subscribe to know when future videos are posted, and thank you for watching.